starting to discuss on membrane for gas separation. This is one of the areas where membrane operation are also playing a very important role. However, it's still different from the success that we have been discussing in the spring on membranes in the treatment of liquid solution. Remember that reverse osmosis or ultrafiltration are today dominant technology, very well accepted, growing very fast, and still a lot of research, but they are very standard in many applications. It's not the same for gas separation. On gas separation, there are a lot of potentialities, a lot of attention, a lot of research in progress. However, except few cases, we still don't have large-scale standard application. There are few situations, for example, the production of nitrogen, what is called non-cryogenic nitrogen, is very well accepted technology, particularly for size of the plant, not the largest one. There are a lot of operation for what concerns hydrogen purification. There are operations for what concerns the separation of CO2 from methane and similar, but far away from the success of liquid operation, liquid phase. The motivations of these are different. There are different kinds of motivation. Some of them are related to the market. You know, in the gas system, there is much less competition than in the liquid system. Gas systems are very big normally, and then we have some dominant industrial groups working in the field. Air Liquide, Air Products, Uber, BOC, etc., huge company, and they just sell gas. Big company. It's very difficult for a small competitor to fight with this big company. And this is also inducing relatively less competition, means also less innovation sometimes. And that's why if big companies don't decide to make this technology standard, it will be much more complicated to have a fast development. On the contrary, there are some areas where everybody is looking with great attention to the potentiality of membrane for gas separation. For example, you heard probably already CO2 capture. This is one of the areas where, in principle, membranes can give a lot of contribution to control global warming, and just by reducing the CO2 emission. And reducing CO2 emission can be approached in a different way. You can try to go ahead having a lot of emission, but you can try to capture CO2 and to reutilize eventually. There are big projects that have been sponsored in some countries, Japan for example, where CO2 can be captured and transformed together with reaction with hydrogen, etc., in some acetic acid or methanol for starting what is called a C1 chemistry. A chemistry competing with this oil chemistry. And that can be related to the capture of CO2 and transformation of CO2. Not yet real, but there are interesting possibilities. Probably part of this thing we are going to discuss today, you have heard something by also Professor Yomoli, because discussing membrane preparation for gas separation. Probably you also heard something about, but we will try to talk with a different approach and different accent, so we will see. I don't know exactly how was done. First of all, here just which are the field of interest, and as I was mentioning, one of the areas where we have many plants around is the hydrogen purification and also hydrogen production. Remember that different with other compounds, hydrogen does not exist free in nature. in largest quantity. So when people are talking about the hydrogen society, that means a lot of hydrogen will be used in the future as alternative, etc. Point number one, we have to produce hydrogen. Hydrogen does not exist. When you are talking about fuel cell in your automobile, instead of putting oil and gas, the first point is where the hydrogen is coming from. Oxygen in the fuel cell you can extract from the air, but not the hydrogen. That's why you have the system today for fuel cell is a complicated system because it's quite sophisticated. Because the first thing you have to do is to find the origin from hydrogen, which are compounds from which you can extract the hydrogen. For example, can be alcohol, can be gas. And that's why one of the reactions is steam reforming of methane, for example. Methane is a gas that we are using already. From methane, through a reaction of steam reforming, you can produce hydrogen. You produce also CO. So remember, we have to try and find a way to reduce the CO content to avoid fouling of the catalyst of the reaction, but has to be produced through steam reforming. All this can be done on board, and we will discuss when we were talking about membrane reactors. You will see that, for example, the production of hydrogen before the problem of purification can be done using, again, membrane technology, because we will make very small reactors on the back of your car, having methane that you can take from the gas station, as we are doing today, and continuously transform in hydrogen, and the membrane reactors will be here for the production, and the purification will be also done with membranes. Palladium membranes will be utilized just to remove at concentration lower than 10 ppm the CO that is produced during steam reforming of methane. Another area of large interest, membranes for the capture and sequestration of CO2 for controlling, I was mentioning before, this problem of CO2 production. Separation of nitrogen, oxygen has been the first area of interest. The idea was to produce an alternative to cryogenic system. The idea was to produce nitrogen and oxygen from air. The system is quite interesting, but with the membranes we have today, still in something the competition with cryogenic system is tough. In some cases, for large scale, etc., still if you have to produce a large quantity of pure oxygen, membranes are not really competitive. You can produce oxygen from air at a relatively low concentration today. For example, for biomedical application, if you go in a hospital, you will see some people that are living with some, they need supply of oxygen, and in the corner of the room there is a small kind of refrigerator, small plant. In this case, are membranes producing continuously oxygen from air. But cost in this case is not an issue. Cost is not, you cannot put a cryogenic plant there. That's why instead of putting tanks, membranes can do the job. Vice versa, nitrogen production is with the same kind of technology. If you're not looking to the oxygen, but you're looking to the nitrogen, this is basically the standard. Huge plant exists around the world already producing what is called non-cryogenic nitrogen, and this is based on membranes because it's much more competitive. You can have a big plant, the separation factor we have is good enough. Natural gas sweetening is another area of big interest. Biogas separation, that means methane, CO2, etc., and conversion, and many other applications of a smaller scale have been tested, have been also utilized, but not in very large scale. Remember that one of the problems at the origin of this not large success at the moment is that people were assuming that fouling problem, for example, and pretreatment for gas separation is not so severe as in reverse osmosis. concentration polarization was not considered a big problem. Fouling, no stability of membrane were not considered a big problem. It's not really so. It's so in principle, on small scale, in lab scale, but when you go in real life, in the petrochemical industry, for example, for the hydrogen purification, people install it, big plant, in big petrochemical company all around the world, in Venezuela, in Italy, in Sardinia, I remember, case which I know personally, and everything that they invested millions and millions of dollars for running the plants. They were supposed to run for years, and after 6 months, problems. And the problems have been very much related to problem of fouling and pretreatment. Because when you install, if you build up from scrap a new company, you take care of all the detail, you can well integrate membrane operation and with the other operations, and you study from the first moment. When you have to install a new operation as hydrogen purification in an existing petrochemical plant, the people doing their job in the other step of the process don't like to change anything. And that's what happened normally in real life, that some of the level of purification they were using before sending hydrogen to the final step, membranes, were not sufficient for membranes. Still unknown in part. The point that membranes, that for example, they are using to remove H2S, to remove CO, etc., from the gas stream. They were using some complexing agents. And they were cleaning with some standard technology in liquid phase, etc. Good for normal chemical reactions and so on. Not good for membrane separation. So the plants, after some time, the membrane that were supposed to live years were living a few months. So we have the people investing in this area were assuming that 5,000 plants were going to be installed in 10 years. 200 have been installed, not 5,000, because for this kind of problem. Still in part to be solved, having better membranes, more stable, or better integration with the technology in the big system. The day that the system will become a standard, so you will install from the beginning, everything will be just well designed. But if you have to enter in a system already existing, it's a little bit more complicated. There is one area that we will mention, quite interesting, vice versa, not represented here, which is the separation of vapors, VOC. There is a lot of plants, not too far from here, in China, for example, in Europe, in which membranes can be utilized to separate, to recovery, monomers that you are present in flue gases, in the gas emission. The problem of PVC production, for example, that you know there is some carcinogenic monomer that were going in the environment, and they're at the origin of a special case of cancer, which has been a big story nobody was aware about, but a lot of people died from this. Today, it's been solved using membranes. Special membrane in which you can separate, recover these monomers, also if they're present in very small percent, few ppm in the emission, but you can recover and reuse. And so the investment is quite good because the cost of these monomers is expensive, so you can reuse in the process. In the meantime, you save the life to the workers around. At that time, when the story started, no one was aware of the effect of these monomers on your body. Now we are, and this is a case in which special membranes, people have just some silicon rubber membranes for the separation of the VOC in gas phase, vapor phase, is very well accepted. The advantages of this membrane operation in the gas separation are the same, basically, that we have been discussing, talking about the liquid phase. No big difference. They are quite efficient normally. They are simple. As everything in nature, the separation is relatively simple, not too complicated. You can have high selectivity and permeability for some specific components. In general, not so high as sometimes people are looking for, but more and more having new polymers, new system, basically low energy compared to the cryogenic system, for example, and the possibility to integrate this operation in other membrane operation, that means we have integrated membrane system as we have been discussing, is also quite interesting also in gas phase, and this is becoming more and more important. There is a less environmental impact. They are all, as all membrane operation, flexible and easy to scale up and also scale down if necessary. This is becoming always and always more important, what we call flexibility, which basically means, first of all, that the same units, same system eventually can be easy utilized also for different separation. Eventually you change the membranes, but you don't have to change all the system. Pumps and racks, they are all the same. But what is more important, that if you have you design a plant for a production of 200,000 cubic meter per day, and tomorrow you want to make double or half, it's very easy. You increase the number of membrane module, or you just make a bypass if you want to reduce the number, the productivity, etc. Very difficult to do something similar with other technology, much more complicated and different. So the flexibility is becoming one of the aspects quite interesting, because we need flexibility today. Things are changing much more faster than in the past. As I mentioned many times, advanced level of automatization, remote control, etc., is quite important today, more and more, because this is a part of the new process engineering aspect. And all these points here, if you analyze carefully, are very consistent with the logic of process intensification that we have been discussing many times. As you can see from here already, there are also, in the case of gas separation, the final configuration of your membrane can be different. You can have a traditional hollow fibers. Hollow fibers are much more present in gas separation than in liquid phase. In liquid phase, as you remember, for example, in desalination, hollow fibers are not very much present for different problems of fouling, etc. In gas, for the reason that I was telling before, traditionally gas are much more clean. There is no particle, or easy to separate. So membranes for gas separation are more important. Big company as DuPont, that initially they were investing a lot for producing hollow fibers for desalination. At one point they stopped the operation, and because it was not convenient, there was a lot of trouble with fouling, etc., but they moved to gas separation. So DuPont today is not one of the companies that is familiar to you in membranes, but just because it's covered. When you are talking about Air Liquide is DuPont. Air Liquide does not make membranes. All the membranes that you have in Air Liquide are coming from DuPont production. The same know-how, the same people that were working to make fibers for desalination, when they stopped desalination, they did not forget about the technology. They just move all this know-how in making fibers for gas separation. The same is for what concerns the other company, Air Products. The two largest companies in the world making gas production are Air Liquide and Air Products. Air Liquide is using DuPont technology in Wilmington, in the United States. The same people, the same research center are working on this. And on the other side, Air Products is not making membranes. Air Products bought a big division of Monsanto, because the first fibers were produced, and the first membrane for gas separation were produced by Monsanto company in St. Louis, Louisiana, and with some guy that was Mary Tripodi, J. Hennis. And one day when the people, Monsanto was not a big producer or marketing gases, but when they start to produce with success membranes for gas separation, the number one, the prism separator, were produced by Monsanto, but Monsanto quickly went out of the business because Air Products bought all the division of Monsanto producing membrane, etc., and they created a company called Permea, which is the one making commercializing all the membrane from Monsanto. So our products is just using the know-how coming from other companies. They don't produce. That's what I told you before. Big companies are controlling the market. And that is a little bit more complicated for a smaller company to penetrate the market because you have to fight with the very big people already selling the final product, which is the best way of doing. Anyway, both of them, hollow fiber or traditional spiral wound, as in gas separation, as in liquid separation, are the configuration more utilized. In the logic of process intensification, remember that all these systems, as in the liquid phase, they just are able to reduce the production cost, the size, the consumption of energy, the waste production, in the meantime increasing efficiency, remote control, information fluxes, which is very, very important today, and flexibility, as I was telling before. And this is a typical example of why people were at one point quite interested, already a few years ago already, but this is not coming from a professor. This was coming from a large company in Europe. This was a traditional company, I think it was DMS, a very large chemical complex, and that is the one running, but the engineers from the same company with experience, and they were very much related to one well-known professor in process intensification, Stankiewicz. They just redesigned this company, introducing integrated membrane operation in liquid, but basically in gas phase. This was gas phase, and that was that was DSM, and that was the final design of the company. You can see much well-looking, first of all, but much more compact and environmental friendly, etc., etc. That was one of the motivation for doing this. Let's skip this for the moment. Again, let's remember, if there's all these nice potentiality, etc., what is these membranes? And now that we discussed already many times, in a simple form, when we were discussing in liquids, I gave you a much more complicated and sophisticated definition, but a membrane is nothing more than a physical device. Remember, physical device. One of the advantages of the membrane operation, the chemistry is in making the membranes. But there's no chemistry in the operation, very much less chemistry. And that's quite important for different reasons, environmental problem and public acceptance, etc. So it's a physical device able to separate selectively one or more components in a mixture while rejecting others. Just to remember, that's for gas separation is okay. However, remember that the real definition of membrane is not so simple. Because as you know, today, we can define a membrane as a physical device that can be solid, but also liquid or gas. We have liquid membranes, gas membranes, solid membrane, able to control and to separate eventually mass. That means components going across, but not only components, can also control the transfer of energy and also of information. So the membranes area is becoming much more sophisticated than just separation of chemical compounds. You can transfer energy across the membrane, you can transfer information. We have today artificial retina, for example, that is one of the systems already running, in which you have a transfer also of information. People are studying the new computers in which membranes will have the function of the chips. They will control this, the information transfer. So it's much more than this. But for a gas system, this definition is sufficient enough. Just to remember that talking about application, I like to remember that today there is not very much as in the liquid. However, the system is changing. People don't realize that there is much more membrane sometimes around that you don't see. People are talking much less. For example, if you take a train in China, not too far from here, and you want to go to Tibet, Lhasa, now they have a train. There was no train until 5 years ago. Now the Chinese government created a new connection between valley, this sea level, and 5,600 meters up on the Himalaya area, which is, is very high. When you travel from sea level to 5,000, you can have a lot of trouble. As the same what happened in the plane. This trouble, you don't feel nothing when you are on the train that is running there. Why? Because on board of all the trains that are traveling in China, in this area, they have membrane system. They just operate by enriching the oxygen of the air when you are going from sea level to 5,000 meters. And so you just live in a much more comfortable area. And this is already running, people don't know about, but this is a continuous membrane system enriching the air in oxygen. The same when you fly in the plane today, not you, but the pilot, as you see, they always have a mask in here, particularly in the jet of the Air Force. And this area, because they just go very high, etc., they need oxygen. And in the past, the oxygen was coming from tanks. No more. All the new jets, they have a membrane system in which what they have, this pilot, what they have in front is just a system connected to membrane system supplying oxygen extracted from the air. So there are situations in which membranes are becoming not big plant, but running already in a different aspect of our life, as to have oxygen when necessary by extraction. In this case, there's no competition in terms of cost, because the alternative, cryogenic and PSA, etc., you cannot go around with a PSA or a cryogenic system. So in this case, if you have to do it, and today we need more and more to do it, membranes are playing the role. So remember jets, or also jets. When you go to the movie, you will not see anymore, there is a helicopter flying, fighting, and big fire sometime when there's these things don't exist anymore. Cannot happen, because all the jet, civil for passenger or for the army, they have another membrane system installed. It's a membrane system in the tank for your oil or diesel, and this is a system in which the reason for the blowing up when bullets arrive was that there is a lot of vapor related to the gasoline, etc., and this will make a big fire. You will not see anymore this big fire, because the system is just neutralizing the environment. When the diesel is going down, nitrogen is going in and making the system totally inert. This nitrogen is coming from a membrane system. There's no tanks just injecting nitrogen. It's just a continuous separation of nitrogen from air that just fill up, save the empty space where was the diesel before. So no vapor that can be easy transformed in fire. And this is another application very standard today. Not visible, people don't like to see this kind of thing. You don't like to see this blowing up of your plane, but that is the way of doing. Also, in the gas phase, we can utilize porous membranes or dense membranes. I don't know if you know that the first large-scale installation, I told you already, of membranes at industrial level was based on porous membrane for gas separation. Which process? Do you know which process it was? Who knows about it? In the last century now, but in the 50s, the 60s, there was one problem. People were planning to create atomic bomb. And for making atomic bomb, you need to have uranium-235. Uranium-235 does not exist in nature. Nature is very smart. They have everything is 238. With 238, you cannot do atomic bomb. But we were trying to make atomic bomb, so we need to have 235. 235 is present in a very small percent in the mixture, in the ores that you extract from land. So what you have to do is to have uranium enrichment. Today, when you read newspaper, there is some country, not too far from here, or not too far in the Middle East, etc., where people are fighting, playing games in uranium enrichment. What they are doing? you have two technology for making uranium enrichment. One is ultracentrifuge, very, very high speed centrifuge in which you can separate 235 from 238. And you need a lot of this centrifuge because the separation factor is still very, very low. The other way of doing, if you can transform the uranium-235 in a gas phase, you can use membranes. That's what we made in Europe. European approach to the problem. In Cadarache, in France, there was a big plant where 5 million square meters of membranes that was sinterized metal, porous membranes made by some metal, have been installed. 5 million square meters, that huge, big amount, because separation factor, again, very, very small, 100 something. And so it was necessary to work in cascade, and there was a huge number of membranes utilized at that time. You cannot find nothing in the literature because that was everything was very secret and not for public discussion. But the first largest installation of porous membrane for gas separation, still before reverse osmosis, etc., was just inorganic porous membranes. I think it was nickel, sinterized nickel. And you can do today porous membranes for some gas separation within ceramic also, in zeolites, and polymers. On the other side, the most traditional and the most utilized today, exactly as in reverse osmosis, big plant, are dense membranes. We will see that the equation controlling the separation factor in dense membranes basically are the same that we are using in reverse osmosis. Solubility, diffusivity, mechanism. Very different when you go in porous membranes, as in microfiltration, ultrafiltration, where we have viscous flow across our pore, and eventually can be viscous, convection, or Knudsen, depending from the relative ratio of the size of the pore and the size of the particle which are inside. So these two systems exist. When you're talking about dense, there is something different from traditional, from reverse osmosis or nanofiltration, because most part of the membranes are polymeric, but we have another family of membranes for gas separation, which are the metal-based membranes. Metal-based membranes is a new area in which one membrane is very well accepted today. If you're interested, shortly, I think in the Netherlands, there will be a big meeting only for discussing metal-based membranes. And this is just this palladium, basically. There is metals as palladium, which has a very interesting property. Only hydrogen can go through. And nature has been doing this way. We have been learning there is a special mechanism for doing this. At the moment is only this metal. In perspective, maybe you can synthesize, you can find other metals. But today, this metal exists, and you can make membranes based on palladium and just use for separation. Why is it important? Because if you want to produce a pure hydrogen, that we were discussing before, I told you you have to remove these few ppm, not percent, sorry, few ppm of CO, and the only way of doing it today, basically, at competitive cost, is using palladium membrane, in which nothing is going through except hydrogen. So all the rest can be separated. And that is the way of doing it, and that's why there are specific conferences and meetings today, for example, in Europe, just in a few weeks, and all ITM is involved. There will be 3, 4, 5 presentations from my younger colleague, only on this kind of membranes, because they are important, are commercially produced, and still expensive, but if you want to purify hydrogen for fuel cell, if you don't use palladium membranes, you don't have an efficient system. This is the definition. Remember, when you are talking about porous, you have to be sure that to use the same way of the same kind of expression. Normally, we assume that microporous means a pore diameter lower than 2 nanometers. Mesoporous is a pore diameter between the 2 nanometers and 50 nanometers. And macroporous is higher than 50 nanometers. So this is better to just to be sure. So normally microporous, the one we normally are discussing, is lower than 2 nanometer. In some cases, you can also have between 2 and 50. Normally we never work on macroporous, is not in our area. That means higher than 50 nanometers. As we have been discussing in liquid phase, also here, membranes is a system in which you can have a selective mass transfer across your membrane system when you apply an appropriate driving force on the membrane surface. And the driving force normally, as we discuss in ultrafiltration, reverse osmosis, etc., in gas separation is basically a difference in pressure. That is the system more traditionally utilized, and in gas separation, sometimes you can have also this partial pressure difference of the single components as a driving force, but basically is the same kind of difference in pressure. That is the typical flow sheet of a gas separation unit, which you can see here. You can have your membranes, and we apply a different in driving force. Delta P is the normal one. You will have your feed and your permeate. And you can use a dense membranes or in general microporous membranes in which solubility diffusivity or Knudsen diffusion or viscous transfer is just controlling the transport mechanism. When you're talking about Knudsen diffusion is transport, a kind of viscous flow in very narrow pore. That's what we define for Knudsen. That means when the pore that we are considering have a diameter smaller than the mean free path length on the diffusing gas molecules. That means in this Knudsen diffusion, the interaction of your particles between particles can be easier than the one with the wall of the system. This length here, the mean free path length, is defined this way. You see, is a kind of a probabilistic equation. This expression is coming from there's a Boltzmann distribution. You can arrive at this equation studying this basic model of ideal gas, basically, and making the calculation of the interaction of the single particle with the wall of the system in which the gas is contained. And that means this lambda is nothing more than Boltzmann constant multiplied for the absolute temperature divided for this 2 is coming from the equation, and diameter of the gas molecules is the D, the hydrostatic pressure is your P, and the K is this Boltzmann constant, and L is the length, mean free path length of the system. Now, depending from the system, you can have a situation in which you have large pore or small pore. And so the difference between the two, in the case of larger pore, the energy loss is mainly related to the interaction of the molecules with each other. The molecules, it's easier for them to have interaction one molecule with another molecule and not with the wall of the system where they are confined. In the Knudsen diffusion is a different. It's much easier to have interaction with the wall and not with another molecule. So in the case of larger pore, the energy loss during transportation is due to the interaction of the molecule with each other. It is expressed in the viscosity of the solution. That's the definition, basically, of the viscosity. Therefore, the flux is referred to viscous flow in which all the molecules transport with the same rate, basically. That is important. All the molecules are going with the same rate. In the pore with a smaller diameter, that is the case of Knudsen diffusion, the energy loss during transport of the gas molecule is due to the interaction with the wall, with the pore wall, and the process similar to diffusion in homogeneous solid phase, and therefore referred as a Knudsen diffusion. So this is the main difference between the two kind of system. And if you want to analyze the Knudsen diffusion, which is the one more traditional in our separation with the pore relatively small, the flux, the number of molecules for a unit of time and unit of volume going across, is linearly proportional to the driving force, your delta P, but is reversed with the thickness of your zeta, but some of these other parameters are present, where this n is the number of the pore. The size of the pore is present. Remember, this 0 to nanometer, or between less than 50, and delta, the zeta thickness. We have to introduce, not in the real membrane, not all the pores are linear, and so you have to introduce a tortuosity factor and the Knudsen diffusion coefficient. So these are all the parameters which are present in as a term of proportionality between the transmembrane flux and the driving force delta P. Increasing the thickness, that means this flux as normally is decreasing in this case, as in normal all the other system, but tortuosity, and sometimes you have also to discuss surface, real surface. When you're talking about membrane surface, the transmembrane flux is not proportional to the membrane surface. It's proportional to effective membrane surface. In your membrane, if there is a pore, only the pore are the one where the penetrant can go through. So if you have a system which is only one pore, big one, is not good at all. We need many small pores for having a Knudsen transport, for example. So the effective membrane surface is one more parameter that if you are going to things very in an accurate form, you have to know the pore size. That's why when you will characterize your membrane, you will also characterize the pore size distribution. You want to know the overall available porosity, which is the configuration. Is just one pore, or is very sharp pore all equal, or there are very small pore and there are many, etc., etc. This can make a difference, and sometimes people don't take care of this. This is if you now want to calculate from the these theoretical gas models you can calculate this Knudsen diffusion coefficient I was mentioning before, and that is normally the expression. That's very important. This is related to what is called also, some of you has to remember when they were fresh student at university, Graham's law. The same law, by the way, the Graham law is very important because the one that was at the basis of the work I was mentioning before for the extraction of uranium-235. And this is written here, basically. The Graham's law is telling that this diffusion coefficient is related to the reverse of the molecular weight, that's becoming quite important because it means that the faster molecules are moving in a different way, small molecules, small means for low molecular weight, are moving faster than big molecules. And that is the origin you can create a separation. And that is quite important, and Graham's law is just telling that there is a reverse of the square root of the ratio between molecular weight of the molecules. Anyway, the Knudsen diffusion coefficient is inversely proportional to the square root of the molecular weight. You will not have to answer to tell me why, because we are assuming that you know why. Because if you go back in the book of chemistry and you read this kinetic model of ideal gas, PV equal nRT, and you apply it to a system with two gases and you calculate this equation is coming true. So don't worry about, but assume that it's not invented. It's nothing more than derivation, simple derivation of the basic PV equal nRT. And that is proportional to the square root of its molecular weight, inversely proportional, to the square root of its molecular weight. So the separation of two gases based on this kind of equation, Graham's law, Graham's was discovered experimentally without knowing any theory of ideal gas, is that you can define a separation factor, selectivity of your gas, proportional to the square root of the ratio of the molecular weight of the gases present in your system. And that's quite important to the point that were able to separate uranium-235 from 238 based on this kind of equation. That's the only case in which large scale this is done, because if you go to put some numbers there, you will see that the distance normally, this separation factor related to this to the molecular weight is not very high. So in real life, you want to separate using Knudsen, oxygen and nitrogen, etc., very expensive, and cryogenic can be cheaper if you don't have biomedical application, etc. But in the case of uranium, that was for making the war, making an atomic bomb. Any amount of money was people were spending. Everything was necessary at that time. So the other way of doing, nothing to do with viscous of Knudsen diffusion, is the traditional solution diffusion mechanism. Exactly the same that we have been discussing when we were talking about the reverse osmosis, in principle. The mass transport in so-called solution diffusion is nothing more than sorption on one phase of your membranes of the various components from the feed mixture related to a partition coefficient, Henry law. That what is happening that you have just to solubilize the component penetrants present in the feed in the membrane system. Can be a polymer, can be a metal, we learn, can be palladium, can be some other matter, can be a liquid, what it is. So you just have step number one, solubilization. That means you will create a difference in concentration between the penetrants in the membrane phase and in the liquid phase. That will be just related to a partition coefficient. This is thermodynamic parameters changing with temperature. At each temperature, you can have your Henry parameter, your partition coefficient. If you change temperature, remember that this number can change and can change also in different way. Normally, you change in increasing, you can reduce, etc., but not 100% of the case. So you have to know the partition coefficient between the gas and the polymer phase, if it's a polymer, the gas and the solid and metal phase, if it's a metal, for example. After this first step, solubilization, you have diffusion of the individual components in the membrane phase according to the activity, the chemical potential difference you have been creating, the activity gradients. And on the other side, and that is the way of doing, that means Fick's law normally can be utilized here. And after, you will have a desorption of the component from the membrane in the permeate gas phase. Remember that this system, apparently simple, is not so simple. If you go in the literature, the diffusion of the penetrant across a polymeric phase normally is described in terms of Fick's law, a linear relationship between the gradient of the driving force and the flux across. There is a lot of anomalous situation to the point that not only the Fick's law, but some other relationships are today utilized. For example, there is one model called a dual sorption model. And the dual sorption model is just telling you that when you have a penetrant that is going in, it's not true that all the penetrant will diffuse across and will be released on the other side. Some of the penetrants can interact with the matrix, with the polymer, and they can slow down. So they can be absorbed and moving much slower than the other one. So you can have Langmuir phenomena, that means some absorption, desorption, and just the free transfer across Fick's law. So it's not always so simple. Normally, we are using only the Fick's law, but a dual sorption phenomena, different mechanisms related to interaction of your penetrant with the system can be also quite important. And today, more and more, because today you are studying, some of you are working in producing membrane where you create cavities and you put some MOFs inside, mixed matrix membranes, particularly in gas phase, where these kind of phenomena are becoming, you create the phenomena on purpose for changing the selectivity, etc. So this kind of relationship that is shown here showing just fixed linear transfer across with the only difference as driving force different in chemical potential is not 100% valid in all the real system. How can we just try to describe the transport phenomena? If in principle, the transmembrane flux, exactly as we made in reverse osmosis nanofiltration, can be proportional to the gradient of the chemical potential of the permeating component. So you can write that Ji is proportional through a phenomenological coefficient to the gradient of the chemical potential. Remember, in the membrane phase, and that's why if you want to make calculation, we don't know the concentration at the interface. We have to introduce partition coefficient, otherwise we are not able to make the integration here. And the gradient, that means the different chemical potential for the thickness of your membranes. This J is the flux, phenomenological coefficient, and the zeta in this case is always a direction perpendicular to the membrane surface that we are considering. And you have this, you can just make some assumption. First of all, we have always to consider that the chemical potential in the membrane surface is equal to the chemical potential in the steady state in the solution adjacent to the gas phase. So at the interface, the two chemical potential will be the same principle. And the change of the chemical potential, the component will be given, that means the variation, the chemical potential will be given to the variation of the activity, of the concentration, for example, and of the pressure. So this is A is the activity, P is the hydrostatic pressure, and this, when you see this sign here, that means partial molar volume. We are talking not the overall volume, but the partial molar volume related to the components I, and that is what does it means this slide here. If you now combine the equation, you make a little bit of algebra. Your J will be again proportional using this last definition to the differential of RT log the activity of the species I in the membrane phase, and this multiplied for delta P partial molar volume of the same species in the membrane phase. And assuming that the membrane, the pressure is constant in the system, delta P equals 0, we don't have any variation, and assuming that this d log I is nothing more than the I in A, we can rewrite the flux in this form here. And so here we are just introducing the gradient in the activity, and now we can integrate across your membranes, and the integration gives the expression of the flux as function of the activity at the interface. So you have Ji is proportional from the integration to RT on the activity of the species site at the membrane interface. That means in the permeates, and that will be in the feed, divided the zeta. Okay? So nothing more than RT on A for the gradient of the gradient of the activity across your membrane from the permeate side to the feed side. This value here is the average activity component in the membranes. Assuming that, as I mentioned before, at the interface gas, the membrane and the gas chemical potential are equal, and so you can rewrite the system, and that is the expression that can become, you can express this as a chemical potential of I at the membrane phase is equal to one standard chemical potential at definite condition of temperature pressure, RT log the activity in gas phase and the activity in the membrane phase, assuming that the two are equal. Okay? And now the partial molar volume, the component normally is also a constant and is equal to the molar volume of the condensed gas. That's why this is the expression that we are normally utilizing. So again, these expressions are very similar to the expression we have been using in RO. Now we can also define here the partial molar volume as a function of the pressure, and assuming that you know this PV equal nRT, that means the ideal law of the gas, we can substitute to the partial volume I, the RT on P,
just from the ideal gas law, and so you can rewrite the expression in this form here. Assuming again that the chemical potential in the membrane phase and in the gas phase are equal, you can rewrite this chemical potential in the gas equal to chemical potential in the membrane phase from these two expressions, and that is the kind of relationship that is coming out. From this kind of relationship, basically, you can show that this term here, this exponential, is always equal 1, basically, and so that there is one more simplification can be done, that assuming that the exponential term, the one I was mentioning here, this exponential term here, is basically approaching 1, is not really 1, but it's very similar to 1. In the first approximation, we can just rewrite our expression in terms of the activity of the membrane phase on the feed and the permeate using these two expressions. The pressure for the activity divided the pressure of reference, and that is the situation that we can have at the end. Now you can introduce, instead of the activity, you can introduce the relationship between the activity and the activity coefficient. Basically, this is molar fraction for the activity coefficient. That means you measure the deviation from ideal properties of the system, and this is in fugacity for these. That's for the liquid phase. You are using the activity coefficient, and here you are using the fugacity, which is the same meaning, deviation from ideal character. And finally, combining different equations, you arrive to an expression of this kind, that the transmembrane flux of one species, I, is proportional through these phenomenological coefficients to this RT on the molar fraction of the component in the membrane phase, multiply for the activity coefficient, for the partial pressure of reference, multiply these two terms, the delta P, the thickness of your membranes, and the difference between these two terms, which represent the driving force of the system. So delta zeta is thickness, this is the fugacity of the system, of the components, the pressure, molar fraction in the gas, and the phenomenological coefficient. You can introduce the relationship between the phenomenological coefficient and diffusion coefficient, and that's the relationship we saw before, Li in azimuth and dc on RT, and the relationship between molar fraction and concentration, that is azimuth, and the molar fraction Ci in the membrane phase is equal to the fraction, the concentration, equal to the fraction, multiply P on Mi. And in first approximation, we can assume that the fugacity coefficient in the feed and permeate are equal. That obviously is an approximation. And you can introduce now Henry law, the sorption coefficient, that is the one that is giving you the partition, the phenomenon of solubilization, basically, which is, this remember, is a thermodynamic term. So here does not appear temperature, because it's, by definition, this number change at each temperature. When you have a partition coefficient, a K, you have only to know at which temperature it is. If you are working 25 degrees, everybody's assuming is okay. But if for any reason you are working at 80 degrees centigrade, you have to find a new K, which normally is not easy. You have to measure by yourself, because you don't find easily on the table. And these numbers are changing. And so the overall flux at the end will be this kind of relationship, which looks, we made all this way through to show you the approximation we have been introducing, by the way. But at the end, you can read again what we wrote at the beginning, that the transmembrane flux J is proportional through a kinetic term, diffusion coefficient, a thermodynamic term, sorption, the partition coefficient K, to the driving force, where delta zeta is the thickness, and that is the driving force, the difference in, this is the molecular weight, and that is the other parameter we've been defining. Okay? In general, when we define about permeability on the basis of this model, remember that the permeability that we define is nothing more than the product of a diffusivity for sorption coefficient. That means it is the product of a term which is a kinetic term and a term which is a thermodynamic term. And that is what basically is what is happening in our system. Now we can define some parameters on the basis of this model. And the parameters we have to remember are more than one, because in literature, sometimes you have numbers, and when you want to compare your numbers with the numbers of other people, be careful which kind of parameter you are using. And it looks strange, but there is a lot of confusion in the literature, less today, but in the past, because people were using different parameters, assuming they were the same. Selectivity is one of these parameters. The selectivity here is defined, the selectivity of your membrane, the one I was mentioning before, oxygen, nitrogen, etc., can be simply defined as the ratio of the permeability of the two species. So that's what we call selectivity, and use of define the separation efficiency basically, and the selectivity of membranes is nothing more than the ratio of the permeability of the single components. If there are only two components, as in the easy case, K and J, the selectivity is defined as the permeability of the A and K. You can define another term, and that is the origin of a lot of confusion, because people think selectivity, separation factor, they look the same, and they are just, I can transfer the numbers. They are not the same, because the separation factor is defined in a different way. For separation factor, what you normally have is, if you have, again, to make easier life, because if you have more than 2 or 3 terms, the situation is still more complicated, is nothing more than the product of the molar fraction of the component J on the permeate side for the molar fraction of the component K in the feed side, divided for the molar fraction of the two components J and K in the feed and then in permeate. So this is quite different as a number. The meaning, at the end, is the same, separation factor or selectivity. If you have a selectivity, oxygen and nitrogen of a certain number, this separation factor for oxygen and nitrogen in the same membranes, roughly, you can have the same meaning. You have to have the same meaning, but the numbers that you are using are different. So you cannot transfer a table of separation factors in a table of selectivity in terms of numbers. In terms of concept, there is no big difference, okay? And so that's the separation, the separation factor is given, remember, from this kind of expression by definition that we are giving to it. The system that normally we are utilizing in gas separation is, again, not too different from the one we are using in liquid phase, basically. Also here you can see on each module we have our membranes, and you can just have a feed mixture of one or more component that we will just send on the driving force in our module. And that was a monodimensional flux is becoming bidimensional, because what is going to happen that there will be some retentate, that means the same feed mixture, enrich in one of the components, but in the meantime something is going across your membranes. Membranes by definition they are permeable. If they are not permeable, they are not membranes, they are barrier, and we don't like to have barriers. So something is going through and you have a permeate. Now you have well defined the concentration. That means you have the flow rate multiplied for the molar fraction in each one of these 3 different streams. The one entering, the one that you call permeate, the one that you call retentate. And this stream has to be interrelated to a mass balance. That has to be valid. If something does not, you don't fit the numbers, somewhere you make a mistake. That means that you cannot, there is a leakage, you are losing some components or something more, but it cannot happen that you increase or decrease one of the components across the membrane if it's not a catalytic membrane. You can also have variation in the concentration, and so apparently this mass balance cannot be true only if you have another component that has been produced during the reaction. I'm telling this because a lot of membranes are catalytic. So it can happen that something is changing, but in this case, you have to find one more stream or something, one more component unexpected that violate the mass balance. If there is no chemical conversion, if no other component is appearing, you have always to find a mass balance in which the initial total volume and concentration has to be subdivided in some components are going in permeate phase in a certain volume, some components are present in the latent state. This equation has to be always valid. If it's not valid, something is wrong in your system, or eventually, something has been happening in your system, and you have to be smart to identify what is going on, and you can find another term here that will satisfy your mass balance. But if you don't find any other term, that is what has to do. So that's your overall your flow stream, the smaller fraction of the component, and these are the different superscript, and this has to be verified. When you're doing now this real separation, there is a lot of factor and other parameters, not only selectivity or separation factor that you have to measure. Keep in mind that the analysis and the design of a membrane for gas separation is much more complicated than the analysis and design of the membrane liquid phase separation. There is much more possibility to change the parameter and to optimize the system than in the liquid phase. So that's why the engineering of this, the engineering science of big gas separation plant design is not so easy. Not too many people expert. You have to know for sure the separation factor or the selectivity, as we learn, for different components. You have a problem of enrichment of a certain component in the permeate or in the latent state. You have to try to measure the recovery of the original feed stream as permeate or latent state, and to check your mass balance to be sure that nothing is lost, etc. You have to control the hydrostatic pressure to obtain a certain level of separation, and the membrane surface necessary. Remember that in the case of dense membranes, and the one we are talking at the moment, we don't have big trouble, because when you're talking about membrane surface, is obvious. When you're talking about the Knudsen or microporous, there is one more correction, because you need to know the effective membrane surface, which is the one where the penetrant can penetrate. And if there is a lot of, if you have one pore relatively big and all the rest is non-pore, it's quite different if you have millions of small pore. So the effective membrane surface is not a negligible parameter sometimes. The crucial parameter you have to consider in the separation, we already mentioned about the selectivity, but there is another parameter that you have to consider, which is the ratio of the feed to permeate pressure and what is called the stage cut. Both these parameters are quite important, and particularly the stage cut. This stage cut we already use when we discuss reverse osmosis, we call a recovery factor. And this is basically equivalent to the recovery factor in reverse osmosis, when we're talking about 60%, 70%, etc. Recovery factor means the ratio between the flow rate of the permeate compared to the flow rate of the feed. And that is one of the numbers that is important, and in gas separation, quite more important than traditionally. The separation factor has been defined, and there is also an enrichment factor that sometimes we have to define, and they are both related to selectivity and to the pressure ratio. This change in the pressure ratio that we have said before is one of the parameters that has been considered together with the stage cut. We can define this separation factor, as was defined already before, but also the enrichment factor. And the enrichment factor, we have to just to consider also the pressure ratio that has been just defined and it is changing with the pressure ratio. We will not do too many plant design, so you don't have to use to make at this stage in this course here too much of this use of these parameters. But when you read manuscript, particularly when they describe you these some plants, etc., you will see that these are the parameters you have to use and to understand what they mean basically. You heard already a lot about the membrane for gas separation, and probably you know most part of these things I'm telling, but quickly, using the few minutes we have, I will just re-summarize some of the points that have been discussed. And I was just also to remember that this is an area where a lot of research is in progress, including here in this department. No one is working on reverse osmosis. No one is looking to produce new reverse osmosis membrane or new ultrafiltration. If we are doing on the side, is because we are also doing membrane distillation, etc., and the same material can be utilized in membrane distillation or also eventually in ultrafiltration. But otherwise, this membrane exists, and we are working more on the engineering, development, etc. In this area, a lot of you are involved in studying membrane for gas separation, to look new polymers, to improve the performance of the existing polymers, trying to understand by simulation how the system works. The problem of the free volume, how the cavities that are present in a dense polymer can have an influence on the final selectivity, etc., is still an open field. The problem of finding better membranes, overcoming the Robinson limits, TR membranes, and so on, just intrinsic microporous membranes, etc., are all fields where there is still a work in progress and going on. That's why, you know, we are working normally with rubbery and glassy polymers. In liquid phase, basically all the work today is basically on glassy polymers, in celluloacetate and aromatic polyamide, etc., because they are much more selective and they are much more interesting in terms of separation factor particularly. In gas, it can be different. There is a lot of work on rubbery polymers, because rubbery polymers have a relatively lower selectivity, but much higher permeability. In a glassy polymers, it's just vice versa. You have a significant selectivity, but a low permeability. Few polymers, as the last one down here, is poly-trimethylsilylpropene, are the one that, in an unexpected way, is offering the possibility to have relatively high permeability, approaching rubbery polymers together with a good selectivity. And that was an interesting case, because when this kind of polymer was discovered, and I've been lucky, I don't know if you know this story, because I've been one of the guys having this polymer in my hands the first time in the world, early in the 70s, because this was discovered in Japan from a student, from a researcher in a company, a very young student. And when he was offering some data, we were sure he was wrong, that he was offering this, the permeability and selectivity, telling that this was interesting glassy polymers, and we were telling, go back in the lab and learn to make the analysis, because that cannot be glassy. This is, with this level of permeability, is rubbery. And he was checking, professor, something, and he was totally right, because this is interesting polymer with a lot of side branch, not that on the chain, that are creating a special cage, etc. And starting from when people understood the morphology of this kind of material, we had a lot of idea to develop other material having the same kind of final morphology, basically. But initially, there was a lot of confusion, to the point that I was confused, telling that the guy was wrong, because it was impossible that this was a glassy polymer with this level of permeability. And in rubbery polymers, basically, you have high permeability and selectivity is relatively lower, and mainly the difference in selectivity is only related to the different condensability of the gas. So that's the origin of the selectivity in the system. The most interesting and more utilized at at industrial level of these rubbery polymers is this polydimethyl siloxane, PDMS. Most of you probably are also, we have here in the lab, the PDMS is utilized in a lot of different separation, including the one I was mentioning before for VOC. The separation of the VOC from air is related to the PDMS. That is an interesting polymer because in this case you can separate the small amount of the VOC are going through much faster than all the rest. So also from an engineering point of view, you don't, if you have a lot of volume, no nitrogen, no oxygen is going through the membranes. Only you can solubilize the VOC, the monomer of this vinyl chloride in the PDMS, and this is going through the membrane. So small concentration, you don't need huge surface because you only extract few ppm of this monomer, very soluble in PDMS. Vice versa, the glassy polymers, they have a high selectivity. In general, also they have good mechanical properties. And in this case, the selectivity is mainly related to difference in molecular dimension and also in difference in morphology. Keep in mind that if you read the papers in the literature, you will find to understand sometimes selectivity between, I don't know, oxygen, nitrogen in some material, which is not clear. They're molecules relatively similar, also in terms of dimension, etc. And you have a separation factor 7, 8, 10, 11. In this case, you have to introduce entropic phenomena because the space configuration of your molecules, when they diffuse in a complicated networks, and they have to make turn right, turn left, etc., the entropic phenomena can have a significance, and you will realize that between molecules as water itself or oxygen, nitrogen, the space configuration is different. And the tortuosity, the possibility to make some movement in this complicated network of pore is related to the entropic effect. There is a paper by Professor Bill Koros or Don Paul that were just related to this kind of analysis. But basically the difference is a molecular dimension. And the problem of this material is related to the existence of this free volume. And the free volume basically, normally in each one of these glassy polymer, we have a certain level of the free volume, that is the order of this 20%, which is basically stable in the structure. And that's the one that permit basically the transfer of the penetrant from one side of the membrane to the other one. And it's quite important, this sentence here, because all these different cage and pore, etc., are normally interconnected. And the low accessible surface area can be measured by gas absorption. High free volume glassy polymers, polyimide, PPO, are normally the one used. This term interconnected is important, I was mentioning, because you will have some lectures in which somebody will describe you how this term has to be today understood better. Because, again, you can have a big high free volume, but if the high free volume, as I was mentioning before, is nice high surface, it's totally different if you have the same final number, but related to many other small free volume linked between some eventually narrow pore, etc. And the selectivity can be related very much or how this free volume is organized. Big cage, which molecules can penetrate, or small cages with some interconnection. And changing this interconnection, that means the morphology of the free volume, you can have totally different final behavior of your polymeric membrane. This is one of the areas in which a lot of research is in progress to predict the final behavior and eventually how to modify the polymer to induce some of this change in the free volume. But we will have some specific discussion on this. To close here, just to remember that for all the polymer, except some special case, reverse selectivity, we will mention next time, but basically the Robinson trade-off is very popular. I think in each lab you have one of these plot on the wall, in which what is happening normally for most part of the separation that we are interested, and for most part of the polymer we are familiar, the selectivity as function of the permeability measured in barriers is following this kind of behavior. Increasing the permeability, you are normally decreasing the selectivity, which we don't like, because we would like to have, as I was mentioning before, was the poly-trimethylsilylpropene, something which you can increase permeability without losing too much in selectivity. This is not the situation. As you can see here for hydrogen methane, hydrogen nitrogen, or nitrogen methane, etc. For all these couple of systems, we have this kind of trade-off. And at the moment, no one is able to modify this. Just to be sure that when you measure this, be careful that you must be sure these behaviors, if you are measuring the permeability, we define selectivity as a ratio between permeability of the two components. So you can measure permeability of nitrogen, permeability of methane, make the ratio, you have the selectivity. You have to define selectivity measured with pure gases. Because when you go to measure the selectivity of a real mixture, you can find different numbers. And that's something, again, introducing confusion in the literature. People were talking selectivity about measuring, just making the ratio between two different permeability measured individually. If you measure in a real mixture of 3, 4, 5 components, quite different numbers are coming out, sometimes because you have to recalculate carefully the vapor pressure, the real composition of the different system in a system, and that can also is not easy. But remember that you have to define or try to understand your colleague what he's telling you. He was measuring the selectivity independently on a real mixture, and try to compare the same number, otherwise there will be some confusion. And that is in much more general case. However, this is only to mention one point. Remember that this trade-off that people for a long time were assuming as something written on the stones is not true. Day by day, we are realizing that this Robinson plot is changing with time. This one was the number 1, but already now we are working in 81 or 88, I don't remember. This the first Robinson plot was modified, and this the other one. And today, more and more, we have other membrane that violate apparently this one as the polymer that people are working in this institute, these TR polymers, and all the matrix, all these mixed matrix polymer, for example, basically violate the Robinson plots. So this is very useful and practical, because a large number of the polymer apparently respect this Robinson plot, but as soon as you become a little bit more sophisticated and you want to do something new, as here in Anyang, all your TR are up here, and the same is up. And the same upper bond is changing. This upper bond is moving updating every 10 years, 15 years, you can find another one. Okay, anyway, we will continue next week. Any question, comment, problem?
So for gas transport, there's diffusion and absorption. Which one is usually the limiting factor?
Which one is the
limiting factor, usually? Like for rubbery, maybe.
Limiting factor in the sense that how we want to increase the
right.
Well, there is no limiting factor here, basically. If you're talking about limit factor as we can have in reverse osmosis, at one point we can have osmotic phenomena that will block the transfer across. Here we don't have, basically.
What I mean is that it first has to absorb and then diffuse, right?
Yeah.
So maybe diffusion is slower than absorption, which
Well,
means diffusion is...
Well, the question is correct, because in fact we have two different categories of membranes. This model, in some case you will find situation in which the controlling factor is different in solubility, case in which controlling factor is different in diffusivity. We can normally what is the really controlling factor is solubility. If the chemical don't solubilize in the polymer, there will be no diffusion. And the diffusion normally is a fixed law in a first approximation, but I was anticipating already that fixed law is valid in general. But if you buy a book, this by what's the name, Crank, by a guy named Crank, the diffusion in polymers, you will find, or if you look in the literature, including check on my name or Offenberg or Don Paul, you will find a lot of anomalous case. So in principle, solubility is the controlling factor, because if you don't solubilize, nothing can go through. And when it's solubilized, fixed law is controlling, and if the size is not too different, diffusivity coefficients, roughly, they are similar. But as soon as you go a little bit more in detail, you will find a lot of cases in which this is not true, because the diffusivity can be anomalous. You can have a situation in which the diffusion coefficient very, very different for different reasons. And for example, the species don't diffuse easy way, but they can be entrapped, block in some case. So Langmuir is not Henry controlling, but it's Langmuir controlling. And so you have a dual sorption phenomena. And the dual sorption phenomena has to do with this change in diffusivity, not in diffusion coefficient, but in a specific absorption or entrapment of the penetrance in the polymer itself. So the system is complicated, and there are a lot of non-Fickian diffusion that can change completely the separation factor. I was telling you before that the system, the gas diffusion is much more complicated theoretically and experiment than the liquid. In liquid phase, we don't have this kind of problem too much. Or if you have, it's because you want to have. In saying you put some penetrance, some matrix, mixed matrix systems, and you add something and you already know the behavior. In polymeric system is a little bit different. Now we know more, but people have to write the books on diffusion in this system, and you will find a lot of dual absorption or anomalous diffusion, where you can have enhancement or you can have decay, depending from the interaction of the penetrance with the matrix. So it's a little bit more complicated then. Okay? I apologize that I have to fly far away, but I'm coming. We will meet next week.